Okay, this continues my lecture on the quantitative use of F equals ma, that is Newton's second law, when applied to basic situations. At the end of my previous video, I went through the basic air track problem. As I mentioned in that problem, the air track problem will become the next laboratory exercise. There was a pulley that was present in that problem. What I want to do here at the beginning of this video is take a look at a problem that examines a pulley in greater detail. Let's go ahead and take a look at the example that I've posted. Make sure that you copy it into your notes. Okay, depicted is what is called an Atwood's machine. An Atwood's machine, before I go further, and the problem is drawn in the following way. Okay, an Atwood's machine consists of a pulley like so, and the pulley is fixed. What that means is that the pulley itself doesn't move up or down or sideways or anything like that. It says that the pulley is frictionless. That means a couple of things. That means that first of all, the axis of the pulley is frictionless, and then there is an idealized string that is draped over the pulley. The surface of the pulley is frictionless. So then therefore, we have a string with one end like so, and another end like so, and then we have two objects here that are attached to this single string. Because the pulley is frictionless, the pulley itself doesn't even rotate. It just redirects the tension force, as we'll see, around a 180-degree angle. Okay, now we are given two masses here in this problem. This mass here, I'm going to call M1, is given to us as 20 grams. And this mass here, M2, is given to us as 25 grams. The reason why I've chosen these values is because I actually have this set up as a demonstration at the side of my desk. After I've gone through the example itself, then we'll take a look at the demonstration. Once again, the Atwood's machine is here at the side of my desk. By the way, we have the word machine that is present here in this problem. Technically speaking, all that a machine really does is that it redirects forces. In this case, the pulley redirects a tension force around a 180-degree angle. In a complicated situation such as a internal combustion engine, ultimately, that's another type of machine that redirects forces. So the basic definition of a machine is that it's some sort of construction that redirects forces. Okay, and then what we're supposed to find here, very simply, is the acceleration of the situation. Okay, now pretty obviously, M2 is going to accelerate downwards like so, and M1 is going to accelerate upwards like so. The string is taut and idealized the whole time. And then basically what we do is we just set up our force diagrams, set up F equals ma, and then go from there. So let's go ahead and do so. So let's take a look at M1 first. Okay, so for M1, we have the tension force upwards and we have the weight downwards, like so. And then the acceleration here of object number 1 is upwards. So then therefore, when I add up the forces here, the tension is going to be positive in the same direction as A, and the force of gravity will be negative in the opposite direction. So T minus M1G is equal to M1A. Okay, there's one equation and two unknowns thus far. Let's now go ahead and take a look at M2. Okay, for M2, we have the same tension upwards like so, and then the weight M2G downwards. In this case, however, the acceleration is downwards like this. So then therefore, when I add up the forces here, the M2G is going to be positive in the same direction as A, and the tension will be negative in the opposite direction. So M2G minus T is equal to the net force, M2A. And then once again, like you saw in a couple of other early examples, we basically end up with two equations and two unknowns, and then we just simply do the math from there. So let's go ahead and do the math. What I'm going to do is I'm going to take this expression here and solve it for the tension, and then plug it into here. When I do, the only unknown that will be left is the acceleration A, which we can then solve for. Okay, so let's solve for the tension. I'm going to move this term here to the other side. I need to do this up here so I have enough room. Like so. Okay, and then we take that green expression for the tension and then we plug it into here. Okay, just be careful to distribute your negative sign through both terms here when we do the algebra. Okay, so M2G and then minus T. So minus M1G minus M1A is equal to M2A on the other side of the expression. And now we just solve for the acceleration A. So to solve for the acceleration A, move this term here to the other side. And I'll also do a little bit of factoring here as I go. So take a look at that carefully. And then let's go ahead and divide the parentheses to the other side to arrive at the following equation. So, and if you compare this expression here to the expression that we saw earlier for the basic air track problem, you'll note that they look similar. All of these pulley types of problems that have two objects attached to each other by means of string, for example, they all kind of work the same way in the following sense. When you derive an expression for the acceleration, you'll always end up with some combination of weight in the numerator divided by total mass. And now let's just complete the example here numerically by plugging in our values. When I do plug in my values, by the way, I do have to convert these masses here from grams to kilograms. The reason why I'm using these masses here in grams in the example is because that's how I have it set up as a demonstration in just a moment. However, let's go ahead and convert these values from grams to kilograms. Recall that there are 1,000 grams in a kilogram, so then therefore what we have to do is divide by 1,000. So 20 grams is 0.020 kilograms, and then 25 grams is 0.025 kilograms. Like so. So those are the values I'm going to go ahead and plug in here. All right, so now I have M2G, so 0.025 times 9.8, minus M1G, so minus 0.020 times 9.8, then all divided by the total mass. The total mass is 45 grams, so 0.045 kilograms. This comes out to be about 1.09 meters per second squared, okay? Easy enough to solve for once you understand the basics of how to set up F equals ma for a situation such as this. Now let me take some time to demonstrate this situation for you, and I'm also going to link it to some of the earlier kinematics that we saw in the previous unit. In order for me to do this, however, I have to move my phone around, so bear with me as I do. Okay, so hang on while I do this. I need to do this without dropping my phone. Okay, like so. All right, so there's the pulley, like so, and then I have my two objects attached to it by means of string, like so. Now, notice that in reality, when I do this, the pulley itself rotates. The reason for that, of course, is due to the friction that occurs between the string and the pulley's surface. We're ignoring that completely. So now what I'm going to do is I'm going to hold the pulley with my hand like so, and the string then just slips over it like so, as is being described in the problem. But I'll demonstrate it, however, normally. Okay, now the easiest way to see this situation that we just calculated is as follows. This mass here is approximately 25 grams. This mass right here is approximately 20 grams. And so then therefore, if I release the objects from rest, this object here accelerates downwards at 1.09 meters per second squared. This object here accelerates upwards at 1.09 meters per second squared. And the situation just looks like this, like so. However, the initial motion of the system doesn't matter, because after I let go of the objects, ultimately what we just calculated on the board happens, and the acceleration occurs as we've calculated. So for example, let's say that M2 here is initially moving downwards, and M1 is initially moving upwards. And then what I'll do is maneuver it such that that motion occurs, and I'll let go of the objects like so. And when I do, at the instant that I let go of the objects, then the situation as we calculated occurs, and the objects accelerate as we have calculated. Now, this object here will hit the desk, for example, at a greater speed when I do this, as opposed to just releasing the objects from rest when I do this. But in both cases, the acceleration is going to be exactly the same. That's rather straightforward. However, watch what happens if M2, for example, is initially moving upwards, and M1 is initially moving downwards, like so. Notice that the two objects slowed down and changed direction. However, once again, as soon as I let go of the objects like so, what we just calculated happens, and the objects accelerate as we do. So this object here has an acceleration vector that's downwards the whole time when I do this, like so. This object here has an acceleration vector upwards the whole time as I do this, like so. So for example, as this object is moving upwards and slowing down, it then speeds up in the opposite direction. The whole time the acceleration vector is downwards at the value that we indicated. Okay? A couple of other things about this example. Let me go ahead and reposition that camera. So bear with me here once again. As I do this. Okay, now, in each of the examples that I've covered thus far, it's been pretty obvious what the direction of the acceleration was for each situation, and then we set up F equals ma, and we just went from there to calculate the acceleration. However, in some cases, it's not immediately obvious what the direction of the acceleration is going to be. So then therefore, what do we do in such situations? I'm going to use this example here to illustrate. Let me do some erasing. Okay, so let's say that we look at this situation here and I say to myself, okay, I think it's going to do this. I think this object's going to accelerate upwards like so, and this object here is going to accelerate downwards. Okay, watch what happens to my equations, that is F equals ma, when I make this assumption. Okay, first of all, for M1. Okay, so we've got the tension upwards, we've got M1g downwards, and I'm assuming that the acceleration is downwards. So now when I add up the forces here for M1 in this case, the M1g will be positive and the tension will be negative in the opposite direction. If you compare this to what I wrote down earlier, you'll notice that these two terms have reversed. Okay, now let's take a look at M2. Okay, tension upwards, M2g downwards. Now we're assuming the acceleration is upwards. So then therefore, when I add up the forces here, I'm going to have T minus M2g is equal to M2a. Once again, compare this to what I wrote down earlier, you'll see that these two terms here have reversed. And then we algebraically combine them together to solve for the acceleration a. Once you do that process, I'll spare you the details. Once you do that process, the acceleration ends up being the following. Like so. And now compare this acceleration equation to what I derived earlier. Notice what happens in the numerator. The two terms have reversed. So then therefore, if I plug in the numbers in this situation, I'm going to end up with negative 1.09 meters per second squared. What do you suppose the negative sign means about this acceleration vector? It means it's in the opposite direction of what I had assumed. So then therefore, did I do the problem incorrectly? No. Leaving the solution like this is perfectly fine as long as you know what the negative sign means. The negative sign very simply means that the acceleration vector is in the opposite direction of that which was chosen. So then therefore, when you approach a problem in dynamics and it's not immediately clear what the direction of the acceleration is, you just choose a direction for the acceleration and then go from there. And then if you calculate an acceleration that's a positive number, then you chose the direction correctly. If you calculate a negative number, then it's just simply in the opposite direction. If it calculates out to be equal to 0, that then simply means that the system moves at a constant velocity. Okay, lastly for this example, before we move on, let's say, for example, that we assume the following. Let's say that I have no common sense whatsoever, and I look at this situation and I say to myself, you know what I think it's going to do? I think it's going to do this. Like so. In other words, the two objects are going to do something like that. If you set up a problem like that using F equals ma, you're going to end up with mathematical gibberish. You're going to end up with like numbers equals 0, and it doesn't make any sense whatsoever. So then therefore, if you set up F equals ma in such a situation, and it doesn't tell you anything, it like leads you in circles mathematically, this then means that it is literally physically impossible. So this situation here is physically impossible. If I take these two objects and then let go of them, it's physically impossible for them to accelerate like so, okay? Okay, there's one more extremely important example for us to look at here in this video. And for those of you that are enrolled in Honors Physics AB and AP Physics C, this will then complete the lectures for Chapter 4. For those of you enrolled in Physics AB, this will then complete the first half of Chapter 4. The problem is what's called the frictionless incline. Okay, let me go ahead and do some erasing here on the board. And then I have to move my file on the screen as well to take a look at the last example here for this section. Okay, so let me move this. Okay, the situation is what is called the frictionless incline. Find the acceleration at the angle of inclination is 30 degrees. In other words, I take an object of some mass m, for example, I place it here on a frictionless incline, and just for simplicity, let's say I release the object from rest like so. We're asked to calculate the acceleration. Okay, let me diagram this out in the following way. Okay, so here's the incline like so, and then right here is the angle theta, as it's called. That's the angle of inclination. That's 30 degrees. And then we have an object here of some mass m. Notice that the mass of the object is not given. Okay, now I'm using my paperclip here to illustrate on this smooth board, and then with this smooth board we are ignoring friction. So then therefore if I do this, after I let go of it, ignoring friction, how many forces are acting on the paperclip? The answer to that question is 2. The 2 forces that are acting upon the object, that is the paperclip, are first of all the force of gravity straight downwards, mg like so, and then we have a surface, so then therefore we have a normal force. The normal force is perpendicular to the surface like so. Now there are immediately some complications here. One complication is the following. The acceleration of the paperclip was down the slope like so, that is, in this direction. Notice that the force of gravity is on an angle with respect to the acceleration. How do we deal with that mathematically? I'll get to that in just a few moments. Before I do, however, I said that the normal force is perpendicular to the incline. Why must the normal force be perpendicular to the incline? Well, imagine what would happen if the normal force was not perpendicular to the incline. Okay, let me write this down. Perpendicular to the incline. And then here on the lower board, okay, why must the normal force be perpendicular to the incline? Well, imagine what would happen if it wasn't. Imagine what would happen otherwise. So for example, rather than being perpendicular to the incline like so, let's say that the normal force vector was somehow pointing at some angle down the incline. Say something that looked like this. Say like so. Where right here is the acceleration. Well, if this normal force was on some weird angle with respect to the acceleration vector, this would then mean that it would have components. It would have a component like this that is perpendicular to the acceleration, and it would have a component like this that is parallel to the acceleration. And then take a look at this component right here that is parallel to the acceleration. What this is literally saying is that the incline itself is somehow pushing the paperclip down the incline. That would look a little strange. That would look, for example, say, something like this. So watch this carefully. Like so. Now, obviously, I'm being a little bit facetious here in demonstrating this in this manner. However, technically speaking, if the incline itself was able to somehow push the paperclip down the incline, that would violate something called conservation of energy, which we'll get to at a later date here in the first semester in class. The energy necessary to do that would have come out of nowhere. I supply the energy necessary to do this in this simple demonstration, but all by itself, if the incline itself was able to push the paperclip down the incline, the energy necessary to do that would have been created. It would have violated conservation of energy. What if the normal force vector was somehow pointing up the incline instead at a slightly different angle? Say something like this. Watch this. So now what I'm going to do is take the normal force vector and kind of point it like this. And then once again, it would have components. It would have a component like so that is perpendicular to the acceleration, and it would have a component like so that is parallel to the acceleration, pointing in the opposite direction. Take a look at this parallel component. This parallel component is literally saying that somehow the incline itself is trying to push the paperclip up the incline. That would look a little strange. I'll use another paperclip here to illustrate. That would look, for example, say something like this, like so. Okay, once again, I'm obviously being a little bit facetious here and describing it in this manner, but once again, technically speaking, if this was possible, it would literally mean that the energy necessary to do that would have come out of nowhere. It would violate conservation of energy. We'll see this in some detail later on this semester. So then therefore, for this reason, this then means that the normal force must be perpendicular to the incline, perpendicular to the acceleration vector itself. So now we go back up into the force diagram that's on the top board. Okay, like so. Okay, now how do we actually then go about solving this problem? Because after all, we still have this first problem of the force of gravity, mg, being on an angle with respect to the acceleration a. So what do? Well, whenever you do have a force vector on an angle with respect to the acceleration, what you do is you break it into components. That's what I was doing on the lower board with the normal force. Now we'll go ahead and do that formally here for the situation as it is with this force diagram. What I have to do is I have to take mg and break it into a component that is perpendicular to the acceleration and a component that is parallel to the acceleration, like so. If I resolve mg into components like this, through the geometry that I'll take you through in just a moment, this angle right here is the same thing as the angle of inclination theta. Let me show you why that is. Okay, so this force diagram right here on this basic diagram for the incline is like so. Here's the normal force perpendicular, and then here's mg straight downwards. So now let me go ahead and resolve mg into these green components. Here, and here, and then right here is the angle that we're interested in. What I want to do is take you through a couple of simple geometrical steps to show you that this angle here is in fact the same thing as this angle. In order to do that, what I'm going to do right here at this point is draw a dotted line that is parallel to the base of the incline. If that dotted line is parallel to the base of the incline, this blue angle theta is the same thing as this angle here, like so. Okay, and now take a look at the blue angle theta and this unnamed red angle right here. What is the sum of those two angles? It's 90 degrees. Notice that the blue angle plus the red angle is equal to a right angle, like so. So this guy here in red is the complement of theta. It's 90 minus theta, like so. But now take a look at the red angle, 90 minus theta, and right here the green angle that we're interested in. What is the sum of those two angles? That's also 90 degrees, like so, right here on the diagram. So then therefore, if the red angle is 90 minus theta, the green angle has to be theta, such that the sum of the two is equal to 90 degrees. Therefore, the green angle theta is the same thing as the blue angle, the angle of inclination. That's right here on the force diagram. There's an easy way to remember this. Whenever you see a situation involving an incline such as this, and you have to break mg into components, what you do is you come down from the normal force and go across, like so. When you do, you then resolve it such that the angle theta is present. And then here's how we add up everything by using F equals ma. Take a look at this perpendicular direction. It is perpendicular to the acceleration. Everything cancels out. So the normal force here does not cancel out with mg. Instead, it cancels out with this adjacent component of mg. The adjacent component of mg is equal to the hypotenuse mg multiplied by the cosine of the angle. Like so. Those two forces cancel. However, take a look at this right here. This component of mg, that's what's causing the acceleration. On this little right triangle, this right here is the opposite side of the triangle, so then therefore this is equal to the hypotenuse mg multiplied by the sine of the angle. That's this guy right here. So when I add everything up in this parallel direction, we now have mg sine theta giving us the net force ma. Like so, and then the mass cancels. Okay, now the mass canceling here is extremely important because take a look at the expression that we arrive at. The acceleration is the same regardless of the mass of the object. Where have we seen this before in the context of class? Galileo's freefall experiment. Recall at the kinematics level, that is in the previous unit, Galileo performed an experiment on a frictionless incline, and his experimental result was that regardless of the mass or the weight of the objects, in the absence of friction, the acceleration of all the objects was the same. That's this expression here. In other words, what we've done is we've used Newton's laws in order to derive Galileo's experimental results. Watch what happens, by the way, when the angle theta here in this expression is not 30 degrees as it is in the problem, but is instead 90 degrees, like so. What is the sine of 90 degrees? It's 1, and then therefore the acceleration is equal to g, 9.8 meters per second squared. All objects follow the same constant acceleration in the absence of friction or air resistance, regardless of their weight. So this is Galileo's free fall experiment explained. That's why this example is so important. And now let's just go ahead and finish the problem, however, and conclude this video. In this example, if you recall, the angle theta was given as 30 degrees. The sine of 30 degrees from basic trig is 1/2. So then therefore, g divided by 2 is equal to 4.9 meters per second squared. But once again, the importance of this problem is that it's Galileo's free fall experiment explained. Okay, that concludes this lecture.